Alright, so our final part of this chapter is to start looking at aromatic compounds. So the previous types of compounds, functional groups, the alkanes, alkenes, and alkynes, are referred to as aliphatic compounds. Aromatic compounds, we've learned, or the aromatic functional group, is defined by benzene. So this compound itself is known as benzene. And so anything that contains a benzene ring, which is this 6-carbon ring with alternating single and double bonds, is known as an aromatic compound. And they have this name aromatic because back in the 1800s, when people were trying to classify molecules, most aromatic compounds were ones that were found to be very fragrant. Now, what makes aromatic compounds unique from most other functional groups is, for benzene, we can always draw a resonance structure. And that resonance structure is where the double bonds are shown as being at the other carbons, or the opposite positions within the 6-membered ring. And it took a long time to figure out, but what they eventually realized was that benzene, or any aromatic ring, isn't actually an alkene. And so if you take some of the reactions we learned recently about alkenes and you try them with benzene, for example, if you take benzene and add bromine to it, nothing happens. And it was reactions like this that made chemists realize that benzene was different. And so what they eventually realized that benzene is that these 6 electrons, and by 6 electrons we're talking about these two, and these two, the 6 electrons of the double bonds, are what we call delocalized. So if we have a normal alkene, like this one, the 4 electrons of the double bond are shared by the 2 atoms that make up the double bond. So this carbon and this carbon. Those 2 carbons share all 4 electrons. But when we say that the electrons, the double bond electrons in benzene are delocalized, what we're saying is that these 6 electrons of the alkenes, or the way we've drawn them as alkenes, it turns out they're not actually alkenes. And those 6 electrons, and sometimes we draw benzene in this way, to designate that those 6 electrons are shared by the entire ring. And one of the ways that chemists were able to prove that, in addition to some of the things that we said about the reactivity of benzene, is the following. If we look at cyclohexene, cyclohexene contains distinct single and double bonds. And you can measure bond lengths. It's something you can do experimentally. And we know that single bonds are not as strong as double bonds, And what that also ends up meaning is that single bonds are longer. The stronger the bond is, the shorter it gets, the more tightly those electrons are being held. And so in cyclohexene, the single bond measures at about 1.54 angstroms, while the double bond, as expected, is much shorter at 1.34 angstroms. But when they decided to look at benzene, they found all 6 bonds were equal to 1.39 angstroms. In other words, all 6 of those bonds were exactly the same. And so this told them 2 things. It re-emphasized this idea of delocalized electrons that we represent here. But it also told them that benzene wasn't an alkene. So these bond lengths, they're too short to be an alkane, but they're too long to be an alkene. So does this mean that the bonds are somewhere in between a single and double bond? To an extent, yes. And it's unfortunately just a limitation on the way that we draw our Lewis structures. But the last thing I want to say about aromatics before we jump into some more specific things such as nomenclature is aromaticity is not just limited to this 6-membered ring. And as we'll see, you'll see plenty of examples in biochemistry. There are many other rings that also fit into this definition of aromatic or aromaticity. And many of those are things that we see in important biological systems.